Hi, I'm Tinyun. I'll present data curation alone can stabilize in-context learning. Nowadays, we have seen large language models achieving amazing performance across different tasks by in-context learning, where we prompt the language models with just a few demonstrations of the task. However, prior work has found that simply shuffling the order of these in-context examples can change the model's prediction. And the selection of in-context examples also has a great influence. To deal with this problem, prior work selects the most similar examples in the training set for every test example. This method can greatly improve the accuracy, but the drawback is now we need to hold the training set around and do nearest neighbor retrieval for each test example. Another way to improve in-context learning performance is to calibrate the model's output probability, basically by preventing the model from favoring a class. In comparison, our work does not need calibration or nearest neighbor retrieval. We show that inside the original training set, there exists a good subset, such that randomly choosing in-context examples from this subset have good accuracy. Let me give an example. So, in the original training set, maybe choosing these red examples as the prompt can get this good accuracy on the test set. But if we choose these purple examples, we'll get very bad performance. In contrast, with our stable subset, no matter how we sample the in-context examples, we can always get good enough test accuracy. The variance is lower here, and the average accuracy is much higher. Here's our setup. Given a large training set and a small depth set, we want to select a subset of 20 stable examples from the training set. In a small depth set, we have gold labels. In the training set, we try two setups, one with gold labels, one is unlabeled. Like here, we just create all possible labels for each example. We call this unlabeled setup because now we don't assume we have a large labeled training set. Here's the recipe for our method. First, we construct a large set of prompt-to-accuracy pair on the depth set. Each prompt consists of k-randomly sampled training examples for k-shot in-context learning. Then, we use the data in the first step to assign a value to each training example. Finally, we select the training examples with the highest value to form the stable subset. How do we assign the values? We propose two methods based on detail sharply and detail models. Both are prior work for detail valuation. We adapt them for in-context learning. Our data models learns a bunch of linear models to approximate large language models' behavior. It's a bit complicated, so we'll just talk about our count-act method here. Our count-act method is very straightforward. In the first step, we have collected this prompt-to-accuracy data. Now, suppose that a training example always have good depth set accuracy combined with whatever other examples. Then we think this is a stable training example and we select it. So the way we assign value to a training example is just calculating its average depth set accuracy. This is our main results table. We evaluate on 5 classification tasks. Each row is a training subset selection method. To evaluate how good a training subset is, we sample 50 prompts from the subset and report the average and worst case accuracy over these 50 prompts. The vanilla baseline here is just simply using all the training examples as the subset. Our methods, count-act, and data models select the stable subset. We also compare with the calibration prior work we discussed earlier. We show that our stable subsets have much better average and worst case accuracy. These rows are the unlabeled setup. Here our method without gold labels even outperforms the baseline with gold labels. Overall, our results suggest that when provided with the curated training subsets, large language models are far less sensitive to the choice of in-context examples. We also show that our stable subsets works well on the out-of-distribution test set. This implies that our methods can identify generalizable stable examples, not just overfitting the source task. Finally, we analyze what makes these stable examples special. Here, each dot in the figure is a training example, and the y-axis is its average dataset accuracy. Surprisingly, we found little to no correlation between accuracy and potential factors like sequence length or example perplexity. Here are some stable examples shared by three large language models, GPEJ, OPT, 6 billion and 13 billions. Please see our paper for more details. Thank you.